All right, well, happy Wednesday, another fun-filled day of vector calculus. Our plan today is to continue talking about line integrals. Where we left off last time, and it was kind of unfortunate where we ended, remember we were doing the line integrals going from one point to another, and we had tried it on a couple different paths, and we kept getting the same number. What I want to do is I'm going to show you how if we change that field just a little bit, then we're not going to see that we get the same thing every time. All right, so I want to do some more examples of line integrals, specifically the vector line integrals, so the ones that we're finding work, right? And then we'll talk about flux, which is another line integral or another application of line integral. So we'll talk flux and circulation. And then we'll start talking about how can you tell when path doesn't matter and stuff like that. So that's the goal. That's the plan for today. But as always, before that, let me open it up to any questions about homeworks or anything like that. Wow. All right, well, that must be because it's Wednesday and stuff was just due on Monday. So you haven't started this next set yet. Anyway,
yeah,
all right.
that's pretty accurate.
You're not supposed to know those things, Bruce.
Yeah, you're supposed to not acknowledge that.
I just supposed to go, oh, it's because everything makes total sense and you guys are just cruising right along. And well, this is the penalty that you guys pay for having someone who's been teaching for over 2 decades. I know the reality. Plus, don't forget, I was a student for a long time too. And for those of you who know me, which by now is all of you, you can imagine what kind of student I was. I would have been that guy. Right. So anyway, so I'm sorry that I acknowledged it. I'm sorry that I peeled behind the curtain and let you see the actual wizard there. So my bad. All right. Well, then let me go ahead and jump to the board and we'll keep doing line integrals. So I'll be right back. All right. So line integrals. Just remember what they are. They're not that really big of a deal. It's just now we're integrating a function over a path, right? We're going to take a function, we're going to integrate it over a curve. And so what they look like, we just have an integral, and we're going to put a big C here to tell us we're integrating over a curve, what that curve is, change. And then we've just got some function. I'm going to go ahead and make it 2D, but it could easily be 3D. But we'll have f of x, y, and then times ds. So just remember that the ds, this is arc length. So we're just adding this thing up as we go along the curve, and we go as long as we're told to do. All right, so this is what they look like in general. But what we saw is that usually we want to convert these into another form. We often use the T, the parameterization bit. And so if we do that, and this is probably the more practical way of doing this, is we're going to integrate from A to B, some f of x of t, y of t. So we'll have a parameterization. And then we multiply this by r prime. Or hold on, no, not r prime. Magnitude of r prime. dt. So this magnitude of r prime, as we talked about, that is the Jacobian. And that's the Jacobian of the transformation from arc length to t to the parameterization. But we also saw back in the day when we were talking about arc length parameter that showed up. Right. So there are your line integrals in general, and then usually what we do when we go to t But then we also saw a specific kind of line integral. We call it the vector line integral. And you'll often hear me call this a work integral. So just FYI, this is what Bruce will say. So I'll put it, Bruce often says work integral. Just because that's what they're usually, well, they're often used for. And in my world, since I straddle the physics world, it's where I always go. So you'll hear me say work integral. What I mean by that is vector line integral. All right, so just be aware that if I say that, that's what I mean. But they're used for things beyond work, not just work. Right? But what we saw for those, like how do those compare? How do those look compared to this? Do you remember what we're doing with a line integral? Okay, so Victor just put big F times prime. Good. That's the kind of the second form we'll get to. But it's actually, again, it's a line integral, but we're doing big F, so this would be a vector field. And we dot it with big T, the unit tangent vector. And that's where the whole work comes from, right? Work is force dotted with displacement. And the TDS is a little displacement vector. T points in the direction that we're going. DS, of course, is just changing its length. DS is really small. It's a tiny little vector, but it's a displacement vector. So we're doing force dotted with displacement, hence work integral, right? But we saw that the more practical form, and this is the one that Victor just put up here, is F dotted with R prime. And the reason that it's just an R prime is that big T, of course, is R prime over the magnitude of R prime, but that magnitude of R prime cancels with the Jacobian magnitude of R prime, goes away. I'll actually put these guys as A and B. But this is the more practical form for that one. Again, we need to parameterize our path. And then we can dot it and go. All right, so this is where we got last time. And we were doing some examples, but I want to do some more examples of vector line integrals because I definitely don't want you to think that you always get the same amount. Because you don't always get the same amount. It really kind of depends on what your field is. So we all get it up to this point, bring it back. We're ready to move. All right, so seeing some thumbs up, thank you for that. So let's go back to that example that we were looking at last time. We were going from the point 1, 0. No, we were going from 0, 1 to 1, 0. Okay, yeah, we were over here. So we were at, wait, which way were we going? Yeah, we're going from 1, 0 to 0, 1. That's right. And we did a couple different paths. The example we did last time, our vector field, if I recall correctly, was y comma x. And we tried it going on a circular path. We did just the straight shot, and then we did the walking along the axes. Well, let's do the same thing. We'll do the same 3, but this time we're going to change our field. Okay, so this time let's make it so that our field is y comma negative x. So it's a little bit different. But we're going to do the same thing that we did before. We'll just set them up for the different paths and see what happens. So for the first path, let's do the circular path that takes us here. Okay, so this is going to be path number 1. So for path number 1, we need to parameterize that curve, figure out what our bounds are, and then put it into the form and do the integral. Okay, so what was the parameterization for that one? What's a good parameterization for the circle? Yeah, we're going to use x equals cosine and y equals sine. So we'll let r equal cosine of t comma sine of t. And for this path, the t's are going to go from 0 to pi over 2. All right, so let's do it. We need r prime. So r prime is going to be minus sine comma cosine. So to do this work integral, this vector line integral, we're going to go from 0 to pi over 2. We need our f in terms of these parameters. So it's y comma minus x. So it'll be sine t comma minus cosine of t. We're going to dot that with minus sine t comma cosine of t. And that's our r prime. And then dt. So before we calculate, are you good with setup? Thumbs up?
Yes, so far.
Okay, good. Good. So we dot this. We get minus sine squared minus cosine squared. Oh, I like where this is going. Because that's just minus 1. So we get minus t evaluated at 0 and pi over 2. And so we get negative pi over 2. All right, so the value of this vector line integral is minus pi over 2. In a real world situation where we've got whatever this field is, so think about this field as it's a force that's being applied to this particle. The force actually did negative work, and negative work is okay for those of you who are not super down with your physics. Negative work versus positive work. Think of positive work is work that's being done by the force. Negative work, that's work done against the force, basically. In the case of like potential energies, we're increasing the potential energy. But negative work is totally fine. But we got negative pi over 2, as opposed to when we had that other field, we got 0. The fact that they're different shouldn't bother you because we're integrating a different function, right? Like not all integrals from 0 to pi over 2 give you the same thing. Duh, right? So it's minus pi over 2. But here's where it's going to get a little bit weird, is when we change our paths, we're going to see that we don't always get minus pi over 2. So here's going to be path number 2. Let's do path number 2 as the straight shot. So we're just going to go straight from 1, 0 to 0, 1. We'll follow that line. All right, so we saw parameterization for this last time. I believe what we used was t comma 1 minus t. And basically what we're doing there is we're just using the equation of the line, right? Y equals 1 minus x. And we're doing the easy parameterization of x equals t, and then y is whatever, with the x's replaced by t's. Now, if we do it this way, do you remember what was kind of funky about this one that you didn't really like?
Integrating from 1 to 0.
Yeah, we were going backwards. This one, the t was going from 1 to 0. Now, we can still do that. It's totally fine. However, it's kind of bad form, honestly. Like the fact that you all were a little bit not liking it back last week, or no, I guess that was Monday. Jesus, it just feels like a week ago. Um, the reason you weren't super thrilled about that with that backward, that's natural, and you should kind of feel a little questionable. So often what we'll do is we'll change these so that we go the other way, so that we can actually go from 0 to 1. But that means that we have to adjust things a little bit. And this parameterization, I'm going to not do this one. Okay, I'm going to go ahead and cross this one off. But instead, I'm going to use the parameterization r equals 1 minus t, comma, t. So what I did right there was, instead of thinking of my x as the t, I'm making my y be the t, because the y's are going from 0 to 1. That's what I want them to do. And so if you take that equation, y equals 1 minus x, you solve it for x, you get x equals 1 minus y, plug in t, boom, you got it. So this one, though, is going to allow us to take t and go from 0 to 1 like we want. I don't know that I mentioned this last time, but the calculation that you do for a work integral, it does not matter the parameterization. I think I did mention that because I was talking about not all parameterizations work and something, but if I didn't specifically state it, as long as your parameterization gives you the entire curve just the one time, right? It doesn't matter how you parameterize it. That all gets worked out when you do the all the conversions. Okay, so any parameterization will work as long as you're getting the entirety of the curve exactly once. All right, but this one should make you feel better because we're going to be able to integrate from 0 to 1. All right, so for this guy then, we're going to integrate from 0 to 1. Our field, again, it's y comma minus x, so that's going to be t comma negative 1 minus t. And we're going to need to dot that with r prime. Well, r prime of this guy is minus 1, 1. So exact same setup. This dot product, if I multiply through, I'm going to get minus t, and then minus 1 minus t, which is the integral of negative 1. Huh. That's kind of cool. We're still integrating minus 1. Coincidence, by the way. But this guy, if we integrate minus 1 and we go from 0 to 1, we get negative 1. So it's negative again. No, that just means that the work is being done against the function, against the field. But the important thing that I want you to spot, notice that it's a different number. There's a huge difference between minus pi over 2 and minus 1. So it didn't take a lot for us to change our field. All I did was I put a minus sign in there. But that was sufficient for it to completely change what we got. All right, so I don't think I'm going to do the third one where we go this way. Just remember that what we had to do there was break it into 2 different pieces. We broke it into the horizontal path and then the vertical path, and so we did it separately for the 2 and then added them. So we could do that again here. We're going to get whatever that value is. But obviously, they're not all going to be the same because these 2 are already not the same.
So which one's the right answer? If parameterization doesn't matter, which one's the correct one?
Okay, so when I say the parameterization doesn't matter, I mean the parameterization for the curve. The answer to your question, rather, of which of these is the right answer, they're both the correct answer. The minus pi over 2, that's the correct answer for the circular path. The minus 1 is the correct answer if we do this linear path.
Got it.
Okay, so line integrals, it does, in general, does matter what path you're taking. Sometimes it doesn't. Like the example we saw last time, where it didn't matter which path we took. That's why you're going to like those kinds of fields. If you can recognize a field that's going to be path independent, you're going to like that. Because then you can choose the easiest path from point A to point B, which might be a line, might not be. I mean, it might have been the circle, who knows? But you can find the easiest path, and that will give you the answer, but only for those special kinds of fields. In general, different paths will give you different quantities when you do these vector line integrals. So what I meant by the parameterization, let me actually just show you. We're going to do path number 2 again. Okay, but this time when we do path number 2, my parameterization is going to be, let's do 1 minus t squared comma t squared. So this one, again, is one that takes us from 0 to 1. Notice that it is going to be the same path, but if we were talking about a particle traveling on the path, what's the difference between these two parameterizations, the red one and the green one?
Just an extra factor on t.
Okay, but what does that mean in terms of an object moving along that?
The speed at which it does it.
Yeah, it's changing the speed. Instead of having a constant speed, like this one has a nice constant speed. We're just constant speed as we're going from one point to the other. This other one, its speed is changing. Right? You know how to find speed. It's the magnitude of r prime. The magnitude of r prime is going to depend on t, which means its speed is changing with time. So we're still moving from point A to point B. It's just we're speeding up as we go. But for those of you, that have done your physics, that shouldn't affect how much work is done. Right? When we talk about work done, it has nothing to do with how fast the particle is moving. It only matters the displacement. Okay, so we do the displacement in less time or more time. Man, work doesn't care about that. Right? So it shouldn't matter. We should get the same value. So let's play it out. Let's see what happens. So r prime is minus 2t comma 2t. So let's set up the integral. We're still going from 0 to 1. But now we're going to have our field. The y is t squared. The x is negative 1 minus t squared. And we're going to dot that with minus 2t and 2t dt. So when I do that dot product, I get minus 2t cubed minus t squared times 1 minus t, or sorry, minus 2t times 1 minus t squared. And if I distribute through, I get the integral from 0 to 1 of minus t squared dt. All right, well, integrate that thing. Minus 2t becomes a minus t squared, evaluated at 0 and 1. Hey, look, it's still negative 1. So that's what I meant by the parameterization doesn't matter. The parameterization for the curve that we're doing doesn't matter. But the path definitely matters. You do a different path, you will get a different value for your line integral.
That makes sense.
Okay. All right. So, in general, make sure you follow the path. Don't just do any old random path unless you know for sure you can. Okay. But I will share with that. I will definitely share with you when you can tell, because again, I'm that way. I'll give you the shortcuts. We're just not quite ready for it yet. All right, so how do we feel about vector line integrals? Not too bad?
Pretty good.
It's all just remember the setup. We're doing f dotted with t, which means if we're parameterized, it's f dotted with r prime, and then go. All right, so that's just a specific kind of line integral. Let me show you another really useful line integral. And this is what's called the flux integral. Now, before we get to flux integral, we should talk about flux, because I know some of you know it from physics, but maybe not all of you do. But when we talk about flux, and it's funny, my brain, I started going to the flow through, because I'm thinking like a marine scientist again. But basically the idea of flux is you've got a curve, you've got a surface, you've got something like that. And flux is a measure, well, let me put on a vector field. So let's say we got some sort of vector field that does this, right? So flux is a measure of how much of the field passes through the curve or through the surface. Okay, so bear with me. So to a marine scientist, fluid physicist, I think of this as how much flows through this surface. If these arrows are talking about how the fluid is moving, flux is telling me how much of that fluid is actually passing through the surface. So what I really need to know, like given one of these vectors, is how much of it is actually perpendicular to my surface. Because it's not the vector itself that tells me how much is flowing through, but also its orientation, right? Like if I have these same vectors, let me draw two vectors here. One of them is like that, and the other one is like that. And they're exactly the same length. The first one, I call this guy number 1 and this one number 2. The first one, all of that vector is pointing perpendicular to the surface or to this line. And so all of it is going through. If you look at that second one, it was supposed to be tangent to the curve, so go with that, it's tangent. That vector, none of it's going through. And so if I have some other vector, so let me put on a number 3 here, something like that guy. Let's try to make it the same length. All right, something like that one. Some of it is going through the surface and some of it is not. Right? So what we really need to do when we talk about flux is look at what's the normal component. What's the normal component of the vector that goes through that surface? Okay, well, if I'm going to do a normal component, what vector am I going to use?
Big N.
The normal tangent vector, yeah.
Yeah, the unit normal vector. So just like the work integral, we dotted f with big T. For the flux integral, we're going to go over our curve, we're going to dot f with n.
Also,
So-
sorry.
Yeah.
Could
Go
we
ahead.
get an example about how this would be used in marine science? Because I've ever only heard about flux in like terms of, like electrical fields. So I'd be interested
sure.
to see how. Yeah.
So I'll give you an exact something that we cared about. So like I told you, what I studied was looking at how tides move sediment. And so you look at the shape of the tidal channel, and that affects your flow rate through, right? And so for us, we'd be looking through for the flux over a cross section of the tidal channel, right? So like suppose that this is a cross section of the tidal channel. Okay, so the water's flowing in and out of the board. So this is like the deep part of the channel. Here's the shallow part. So the shoreline is over here, right? So we're looking at this, right? So flux would tell us a bunch of things, but basically here's our surface. Think of the whiteboard as my surface. I would want to look and see how much of the flow is going perpendicular, going up and down stream on this current.
And that would allow you to determine how much sediment is being carried by the tide.
Yeah, it helps you calculate sediment flow rates. You can also use it for like salinity distribution. Like I didn't do this, but I had friends that did because we did stuff with estuaries, and estuaries are where rivers meet oceans, right? And one of the big things that you worry about with estuaries is salinity, because you got fresh water and you got salt water that are mixing and all that. And so depending on your flux, that would help you figure out how much salt is moving in the various areas. So you'd figure out the flux of the flow and then multiply by a salinity factor to get flux of salt or salinity going through, right? So you do that for salinity. If you are a biologist, something that you're going to worry about is probably like O2, right? How much dissolved O2 is in the water. So you could be looking at O2 flux, right? So there are all kinds of different things that you could look for. But again, flux is how much of that, whatever thing, is passing through this surface, right? And so for me specifically, we always looked at surfaces as cross sections of the tidal channel, right? So we would mark them off. You'd start, well, we're going to meet where the ocean actually starts. And then we'll go inland. There are going to be another one, another one, another one. We would do them fairly regular distanced, right? So every couple hundred meters or kilometers, depending upon how big or how far it goes in. And you would calculate your cross section, and then we would try to model the flow rates. So then we could determine flux and.
All right, that makes a lot more sense.
That-
That makes
that kind of-
makes sense that it's not like a literal surface like it is in with electric fields. It's like a
Yeah, right. Well,
like
and
cross section.
even when you talk about that in E&M, it's not necessarily a literal surface still, right? Like you can create Gaussian surfaces that aren't an actual object, right? But your point is well made, though, that it often is a surface. We're looking at how much of flux is going through this metal sphere
Yeah.
that we got, or whatever, right? So yeah, it doesn't have to be a literal surface. It can be a man-made surface, we're not doing this kind of flux integral right now, by the way. We're not looking through a surface because that's a multi-dimensional. We'll talk about that later this quarter. We're looking at going through a curve, but this line, it doesn't actually have to be a wire or a rope or a spaghetti noodle or anything like that. It can be just a line that we envision in our mind, right? Where we've got, okay, well, we've got this field, this magnetic field. What's the flux through? A circle. Not necessarily like a metallic ring, but like, no, just that circle. What's the flow rate through that?
That makes a lot more sense. Yeah.
But yeah, so it's not an actual surface. Because if you have an actual surface, that usually stops your flow rate, right? Like a dam. You put a dam in there, you don't have to worry about there's going to be no flux because the water won't be passing through it. Anyway, all right, so check it out. It's exactly the same form. Exactly the same form as what we were just doing with work, except now we've got big N instead of F, or instead of T, big T. All right, so yeah, there we go. Right, but we should probably get to the what's the more practical. What about the when we change it to T, right, to little t? So let's look at that. Let's look at how we can change this so that we get one that instead will be an integral from a to b of something dt. Right, that's our goal. We want to have the more functional one. So clearly, we need to know the equation for the surface that we're going through, or the curve that we're passing through, that we're looking for the flux through. So we're going to have to be able to parameterize it. Let's just call it R. All right, so the field itself will do what we've been doing, which is change our x's and y's using those parameters. But then we have to get n. So what's the process for finding big N?
T prime over the magnitude of T prime.
Okay, so we got to get T prime and divide by the magnitude of T prime. So to get T prime, what do we have to do?
Find R, and then R prime.
We got to do R prime, divide by its magnitude. Yeah, finding N is tough. We already know that. We've seen that. Okay. Thank you, Victor. I don't know if people just saw what Victor put in the chat. He said, but if it's in 2D, it'll be easy because of that trick. You guys remember the trick?
No.
Okay. How about, do you remember that there was a trick?
I remember that there was a trick. I can't remember what the trick was.
Okay, well, we'll go with it. There definitely was a trick for 2D. And Victor just put it in there. You flip the coordinates, you flip the components, and then you change the sign on one of them, right? So we already saw that there is a way to get that a little bit faster. We're going to make use of that because it is 2D, because it's a flux integral. And I mean, I should probably put here over a curve. Because if it's over a surface, we're not going to be able to do what we're going to do just right now. Okay. But if it's a curve is two-dimensional, right? It's a one-dimensional object that lives in a two-dimensional world. Okay, but we're in the 2D world. We don't need a third dimension. So we're going to be able to pull this trick. All right, so here's what we're going to do. The F, yeah, we're going to do the F of x of t, y of t like we normally do, right? And we're going to dot it with this guy, big N. Okay, so to do this little trick, here's what we're going to say. We're going to say that, or at least this is the book notation. We're going to let little n, this is going to be the vector in the direction of big N from quote unquote the trick. I'll remind you the trick in a second. Okay, but we'll just call that guy little n. So when we swap the coordinates and change the sign, that's little n. So what we're going to have to do then is take that little n and divide it by the magnitude of little n. Because that'll make it so that it's magnitude 1, so it's a normal vector. And then think about for the ds. What do we have to do for the ds? Well, the same thing that we did before, which is going to be the magnitude of r prime times dt. So I know it doesn't really look pretty, but I mean, it's basically the same thing that we did with the other ones, with the work integrals. It's just instead of t, we're using n. Okay, well, let me remind you then how we get n. So if we've got r, r is going to equal x of t comma y of t. All right, so n. To get n, we need r prime. Because r prime is pointing in the direction tangent to the curve. And we know the one that's normal to the curve has to be such that its dot product with this r prime is equal to 0. So for n, what we're going to do is we're going to swap these guys. And then we have to make one of them negative. Which one?
X prime of t.
The x prime?
Yeah.
Why?
I just felt like it, honestly. I didn't have a reason.
That's cool. That works. Because it could be either one, right? It could be either x or it could be y. Well, think about it as a picture. So here's a path. Here's r prime. Right? And so we need one that's normal to this. And remember, big N points towards the center of the curve, the interior of the curve. So this is the direction we need to point. So thinking about that one, we've got a positive x going this way, but now our y has to go down. So that's why it becomes the negative x. And it turns out that it doesn't matter the orientation, it still plays that way out plays out that way. Like if this is our r prime, then our n has to be here. And notice that our y is opposite of the x, right? So we're going to go ahead and use the negative x prime. All right, so there's our n, no big deal. But check this out. Look at what the magnitude of n is. It's going to be the square root of y prime squared plus x prime squared. Because the changing of that sign, that negative, just becomes positive. And notice that that's exactly equal to the magnitude of r prime. So do you see why that's nice?
Yeah, we can get slash happy now.
Totally. These guys, the magnitude of n and r prime are gone. And now this form, easy peasy. And in fact, if you compare that to the line integral that we used for work, look at how similar that is. This one, we've got f dotted with n instead of f dotted with r prime. But that should make total sense. Because
Also, f still equals y comma negative x.
The n, yeah, it's y prime comma negative x prime.
I meant f. It's still equal. It's still the vector y comma negative x, right?
Oh, no. That's going to be whatever field we're using. When
Okay.
I did that example, Jordan, with y comma negative x, that was I gave you a field.
Oh.
But this field could be anything. It's like when we just write the integral of f dx, that f changes. So does this big F.
Ah, I see.
This big F will change depending upon what field we're looking at, and n will change depending on the curve. Does that make sense?
Yeah, that makes sense.
Okay. All right, so yay. It's virtually the same form, just as easy. It's just a matter of, well, setting it up and doing it. So let's go back to that field, y negative x, and let's look at the flux through that curve, that circular arc. All right, so we're going to go back to this guy, where this is our path, that's our curve. And again, let's go with f is equal to y comma negative x. But this time, let's calculate the flux. All right, so here's our process. Again, start by getting R. Well, we've only done this thing a million times. R is going to be cosine comma sine. All right, so that means we got to find n. Well, we're going to get to n by doing r prime. So r prime is negative sine t cosine t. So then n, this is where we're going to swap. Okay, so we're going to bring cosine of t, we're going to bring that out front. And then we're going to have negative sine of t. So the way that we're going to do this so that it always works, the trick is to take our n, or r prime, swap them, and change the sign on our y. Okay, so that makes this one cosine comma sine. The fact that it equals r, pure coincidence. Pure coincidence. Just because of the fact it's a circle. But other paths, that will definitely not be the case. All right, so let's calculate our flux. So we're going to integrate from 0 to pi over 2. We're going to take our field. If we convert it, it's sine t comma minus cosine t. And we're going to dot that with n. And then we're going to integrate that with respect to t. Okay, so this is still f and n. F dotted with n. So before we calculate the integral, we okay with the setup?
Yeah.
No?
Yes.
All right, so 0 pi over 2. Sine times cosine is sine cosine. Minus cosine times sine is minus sine cosine. So we're integrating 0, which gives us 0.
which makes sense, right?
So that tells us that the net flow through this curve is 0. And that's okay. You can definitely get a flux of 0. That can happen a lot of ways. Flux, like work, can be positive or negative. It can also be 0. So let's maybe talk a little bit about what those different things mean: positive flux versus negative flux versus 0 flux. But regardless, this one we got 0 flux through that surface. Okay, so here's just how kind of flux plays out. If flux is greater than 0, that means that there's the net flow in the direction of the arrows. Okay, so like, yeah, I don't like how this is going. I don't like that. Let's do this. Let's start with what 0 flux means. No. Okay. Positive flux, negative flux is just different directions. Let's just go there. It's different directions. So if we had a curve, let's say, and let's say that this was our flow, this is going to give us, let's say, positive flux. We're saying that that direction is positive. If I had a flow that was going the other way, that one's going to give me negative flux. Okay, it's just like positive and negative numbers. They mean one way or the other, right? Positive velocity, negative velocity, positive flux, negative flux. Basically, you set this direction gives me positive. And then if you get negative flux, it's actually telling you it's going the opposite direction. Let me give you let's go back to that context I was telling you about, like the flow through a tidal channel. What I might say is, okay, I'm going to make it so that going south is positive. So if the flow is moving in the southerly direction, then that would be positive flux. If the flow came in a northerly direction, that would be negative flux. That's it. Okay, so plus or minus just tells you direction. So 0 flux can mean one of two things. The first is that whatever flow we've got going one way is countered by flow coming another way. Right? And so that could easily happen, like in the case of like this. Let's say that this is our surface. And let's say we've got a vector field that does this, and I'm going to just change color because I want to be able to reference them, but these are all part of the same field. Okay, so imagine we are looking at the flux here. Since all of these arrows for this field are perpendicular, we get the entirety of them. We don't have to worry about portions. And basically what's happening is every vector that's in the red direction is being countered by an equal size vector in the blue direction, and they would negate each other. And so we would say that the total flux through this surface is 0. All right, so that's one of the two things that can happen if your flux is 0. It just means that the net flow is balanced. Whatever's going one direction gets canceled by something coming the other direction.
Would another example be a point in space that is experiencing an electric field of opposite charges of equal magnitude? The net flux would be 0.
If we're going to talk about electrical flux, yeah, don't say a point though, but yeah, if we had some sort of a curve or surface that was experiencing counteracting positives and negatives charge, absolutely. Yeah. Yep. And you could think about that. I mean, you could picture an electric field having this, right? So basically think about how electric fields work. They're telling you what happens when you put in an electron. So these blue ones, it's saying the electron's going this way. The other one, the electron's going down. And so if you were to think about being at this point, it's feeling a pull up and a pull down. So it's feeling a pull and a push, positive and a negative. Right, so yeah, the same kind of thing would happen. All right, so that's one of the things that can be giving you a zero flux. But there's another way you get zero flux, and that would be if your field vectors are always pointing tangent to the curve. Do you see why that would lead to zero flux?
Yeah, because none of it would be passing through the surface or curve.
Right. If all of those vector fields, or if all those field vectors are always parallel to the path, by definition, if they're parallel, they can't be perpendicular. So nothing would be passing through. And that's what's actually happening here. That's why we're getting zero. Because look at what our n was. Actually, no, let's look at our field. So our field was y comma negative x, right? If we convert that using this r, that gives us f is equal to sine comma negative cosine, right? So those are our field vectors. Notice how those field vectors compare to r prime. What's the difference in those?
The signs are swapped.
Okay, so the signs are swapped, which means that arrow is just pointing the opposite direction. Okay, so the field vectors are pointing the opposite direction of the r primes. Well, what direction do the r primes point?
Tangent to the field vectors.
They're tangent to the curve. Okay, so there's r prime, which means f pointing that way. So at every point, f is actually tangent to the curve. So that's why we ended up seeing a value of 0 for this one, is not because the flows are canceled, that we're getting positive and negative, and it all cancels. Nope. It's that literally there is no flow through this curve. If this were a, let's say that this field was showing us how something's moving on the surface of water, basically you would drop something in there and it would just go around in circles. It's just going around in circles in the opposite direction. And so if we're going to say, well, what's the flux, what's the flow through the circle? The answer is going to be, well, there is no flow through that circle because the flow is the circle. I don't know if that just made sense. When I just got done saying it, I just went, oh, that was bad. Everybody just probably got lost.
No, that makes sense, because if you drop something in water and it just continues in a circle, it's not going anywhere, you know?
It's not going through that circle.
Yeah. It is
not
the circle.
If we were to like draw a circle there, you would never see anything go past in or out of that circle. It would just sit on that circle. Or if it was inside that circle, it would stay inside that circle. If it was outside of it, it would stay outside of it because it's just moving in a circular path. So anyway, so this is a flux integral, just like a work integral. It's another line integral. It's just a specific type, right? And compare it to a work integral. They're the same kind of form, just slight variation. We're just dotting with something different. right? The one is F dotted with R. The other one is F dotted with N. All right, so how do we feel about that?
I have a question for you.
Yeah, go for it. I'm just grabbing a drink over here, so go for it.
Is gravity a measurement of flux when it comes to the fabric of space and time?
Let me think about that. Well, okay, the easy answer to this is no, but I don't want to just stop there. Because what gravity is big F. Okay, and so a field is never flux. A field, though, can create flux. So the real question you're asking is, what is gravitational flux?
I guess so, yeah.
Okay. And that's why I didn't want to just go, yeah, no, and blow you off. So the real question is, what is gravitational flux when it comes to space-time? And my answer to that is, I actually have no clue. I have no idea. I can't even imagine what that's a measure of, except I can tell you that, like, when it comes to gravitational flux, we always know the direction of it, right? But for every gravitational flux, there's a counter gravitational flux, because gravity requires two objects. You know what I mean?
Yeah.
So that's a good question, but I think I'm going to have to just tell you, yeah, I'm not sure.
Okay, I can live with that for now.
I hate doing that to you, but hey, the world is the way the world is. Things don't always happen the way that we expect them or want them to.
No, this is really off topic, but maybe that's where dark matter comes into play.
Possibly. I mean, yeah, we don't really know a lot about dark matter, obviously.
Other
Yeah,
than
maybe.
its effect of gravity on a galaxy.
Right. Yeah, no, I mean, we know that there's mass out there that we can't account for, that we
Yeah,
can't see,
yeah.
right? And so that's the dark matter. But yeah, I don't know. That's a really good question. Ask Kathy. And that's not a joke. I'm honestly interested to know what her response to what is gravitational flux.
Okay.
Like, what does that mean in terms of the universe? Because she's more likely to have an answer to that than me. So, but please ask her and then let me know,
I will do.
because I'm definitely interested. All right. So let's talk about those places where, oh, no, hold on. Before we do that, I want to do one other curve. We're going to calculate another flux integral. But this time, let's do that same line curve that we did before. All right, because I want to show you that we're going to get a different number. The same thing is true about flux as it was with the work integrals, is that you will get different values almost always when you change the surface. Okay, so let's just see what kind of number we get if we do it this way. So this means, of course, we have to change our R. And let's go back to that parameterization where we can go from 0 to 1. So I'm going to use the parameterization 1 minus t comma t. So R prime, that's going to be -1 comma 1. So what's that make n?
1 -1.
Close. It's going to be 1 -1. We change the value on the y. So it's actually going to be 1, 1. So we don't just swap them. We swap them and then change the sign on the y. All right, so there's n. So then our field is going to be t comma negative 1 minus t. Again, it's y negative x. So I'm going with the y and the negative x. So this is what our flux integral is going to look like. We're going to be integrating from 0 to 1. Those are the t values for this path. We're going to take f, so t comma t minus 1. We're going to dot it with 1, 1, and then do dt. So that's going to be the integral from 0 to 1 of 2t minus 1 dt, which is t squared minus t. Oh, I totally lied to you. Only got 0 again. Oops. I wasn't expecting us to get the same value. All right, so through this surface, we also got a flux of 0. But that's okay. This is a good teaching moment because we're getting 0 for a different reason now. This is the case where the amount that's going through perpendicularly cancels itself out. Some of it's positive and some of it's negative. We know for sure that the vectors, the field vectors, are not tangent to this. I mean, I can show you really easily because remember they were tangent to the circle. So that means like at this point, my field vector is pointing down. Over here, my field vector is pointing right. And so what we're really calculating when we calculate the flux is the perpendicular component of those. But even with just these two arrows, you can see that the one of them is pointing up to the right, the other one is going down to the left. And those are going to negate each other. One's going to give us positive, the other's going to give us negative. And the same thing's going to happen with all the points as we work our way to the center. So a different surface still got us a 0 flux, but for a different reason. All right. So there's flux. The one other thing I just want to mention before we move off of this, off of the idea of flux, is what we call circulation. And circulation, we're going to show that with an integral that looks like this. And I think I hinted at this before, but anytime you see this integral, or this kind of integral, this means that C is a closed path. I was going to write loop, but loop makes people think circles. And it doesn't have to be a circle, it just has to be closed. So if we were to say, try to find the flux or line integral or whatever for this path, we could actually use this symbol. This symbol would say, okay, we're going to integrate over the entirety of this curve. So you could calculate the work done over the entirety of this curve. You could calculate the flux over a closed surface and so on. But when we talk about circulation, if we're specifically looking at this guy, that's circulation. All right. So just realize that if you ever see that term, let's call it the circulation. We'll see a little bit more later. As we go through chapter 6, you'll start seeing how flux is related to there are these other quantities. We're going to talk about the curl of a vector field. We're going to talk about the divergence of a vector field. We're going to see how those relate to flux, work integrals, and all that. So this will make more sense. But just realize in your homework, because I know there's some homework questions. Jordan popped on earlier and was asking me about this. When you see circulation, it's just saying, hey, do it over a closed path. You don't change what you do. It just means that path is closed, which means you might have to change the parameterization. Like if it's a circle, okay, so we go from 0 to 2 pi to finish it off. If it's this one, we would do 4 different integrals, one for each of the sides, and so on. All right, so yay, line integrals. Well, what I want to do now is show you, actually check that. I don't really have enough time to go where I want to go. So what I want to do now is call it a day. So what we'll do next time on Friday, a couple of things. First, I do want to have a quiz. We're set for a quiz. I do want that to occur. In terms of what's going to be on that quiz, let's make it the first 2 sections of this chapter, which is what, chapter 6. So on Friday, there's going to be a quiz on 6.1 and 6.2. All right, so it's line integrals, basically, right? Line integrals and fields, right? 6.1 was just fields, and then 6.2 is about line integrals. And I'm sorry, somebody just said something.
I just said fields, so
yeah.
I don't know if that got picked up.
Yeah, that must have been what I heard. Yeah, so it's fields and line integrals. So we're going to do that at the normal time. So we're going to start that at 1. Has to be submitted by 1:40, and we'll start Zoom class again at 1:40. Okay, so by this point, you guys should be good with that. And so at 1:40, we'll pick up and keep running with this idea of line integrals, but I'm going to show you the faster, easier way of calculating line integrals when we have nice fields, because some fields are really nice, and they are the ones that we saw a little bit ago that we call conservative fields. So we'll spend some time looking at conservative fields and what we get from those. Basically, we get awesomeness from conservative fields. You're going to love conservative fields because it makes doing a lot of these integrals fast, easy, sometimes even trivial. Okay, but again, special case. All right, so that's our plan. That's what we're going to do on Friday. All right. So any last questions here before I hit the stop record button? All righty. So I guess I will see folks on Friday.